You guys know what this music's from? Hint. It's a very, very good game. A very good game that has a remake that just came out. Yes! Final Fantasy VII. I don't know if they're keeping all the original music in the remake. They're probably redoing the music, you want to get it, but they're also splitting it into 3 games. Yeah. I do want to get it. I heard at least the first installment's really good. I wonder to what point in the game the first one goes. How's everybody doing this morning? Feeling a bit sick. Sorry. I hope you feel better soon. I'm feeling good. April 20th. That means last day of class is officially May 8th. We only have 3 weeks left of classes. I know, 420, right? Thank you, Hillary. You guys like the Willie Nelson braids? Braid game is strong today. Snoop Dogg's birthday. Dude, Snoop likes to wear the braids. In honor of Snoop. Three weeks before we were thrown into the fire of professional work life. Oh man. Looking like a brunette Legolas. Nice, Sean. Yeah, it's an interesting time. Because I think it's, you can hear the music, but you can't hear me talking? Is that true? You guys can't... Can you guys hear my voice? You can hear me fine? I'm looking at my sound bars. The balance seems pretty good. Okay. Are you guys ready to talk about estimators? I had said I would play a song before the class. Well, we got to get started, so maybe I'll play a song after. But let's get started. Let's get into this. I'm going to turn off the chat on the side, but I'll keep. Opie says his voice is like a fly going by the mic. I think it's just you, Opie. You got it? Okay. So we're going to talk today about the prediction state estimator. And I think this is a really, really cool topic because we know that for a feedback control system, you have to measure the output or you have to measure something so that you know how close your actual system is behaving compared to how you want it to behave. But you can't measure everything. Or maybe to measure a specific something, it requires a very expensive sensor. So the role of an estimator is to estimate things that you're not measuring. And guys, estimators are everywhere. They're on your phone. They're in the car you drive. Probably in the temperature control of any building. Anything with an automatic control under your bed. I mean, it could be. Anywhere you have an automatic control system that's using state feedback, and modern days, a lot of control systems use state feedback, probably the majority. So there's going to be estimators in there. Now, to introduce the estimator, I'm going to bring us back to this inverted pendulum on a cart system. Opie, PID is very popular, but I'd say state space is even more so. All right. I've done this recap before, but we're going to run through it again because it's been a little bit. So let's say that we have this inverted pendulum system, and the only thing we're measuring is the pitch angle. And then, so we'll say this is equal to Y, our output. Let's just have one output. And then the way we're controlling this is we're shifting this base back and forth to try to keep the pendulum upright. And we're controlling the acceleration of that base. So we'll say the control input U is the lateral acceleration. Now, we need a model. So if you were to use physics, so mechanics, Newton's laws, you're going to come up with a second order continuous time differential equation right here on the right. If you use small angle assumptions as well to make sure that this is a linear model. This x double dot, that's the acceleration of the base, which is the same as u. Now we're doing a digital control system, so it has to be in discrete time. The best way to convert to discrete time is first to convert to a continuous time state space model. There's an infinite number of ways to define your states. But a popular technique is you just take your continuous time model and you set your states, let's call them x1 and x2, equal to your dependent variable and just subsequent derivatives of that. So like theta, theta dot. So there's two states here. And then once you define your states, you can put it in this matrix form if it's a linear state space model. And in this class, we're just dealing with linear models. So you can put it into this. Oh, I changed my variable name. Up above, I said the states were x1 and x2, but in this picture, there's z1 and z2. Don't be confused. They're just states. So if you assemble these equations in matrix form, you get 4 matrices: A, B, C, D. AC is the system matrix, BC is the control influence matrix, C is your output matrix, D is your direct transmission matrix. We've defined these before. D is usually 0. And once you make these matrices, it's real easy to convert this into discrete time. So these conversions are in the table below. It depends on your sampling frequency as well. So we were assuming here that we update 20 times a second. So your sampling period in seconds is 1 divided by that. And A, B, C, D, these are your discrete versions of those continuous time state space matrices. Okay, so you use these formulas, you get a discrete time model, A, B, C, D. So you got your output at every time step is related to your states and your input through that equation, and your states evolve according to this equation. Is there any systems you can think of where D would be non-zero? D is non-zero if your measured output is proportional to your input. So I can think of a system. Let's say you're measuring the acceleration of a cart. Okay, so you can use an accelerometer to measure an acceleration. And let's say your input is a force to the cart. Acceleration is directly proportional to force. So in that system where an input is a force and an output is an acceleration, D would be non-zero. Because you would have your acceleration is, oh, my pin just, acceleration is somehow proportional to the force. So maybe it's not as rare as we think, because that sounds like something that could easily come up. Okay, so this first step up here is just getting a discrete time model. So I'm just blazing through it because it's recap. Now, let's say we want a state feedback controller. In this case, first you always start with some performance specifications. So I think I specified a settling time of 1 second. So T sub S equals 1 second. And I said our overshoot is approximately 20%. So if you try to push this pendulum over, it's going to correct itself in 1 second with a little bit of overshoot there. And the target poles that correspond to this condition are these complex conjugate poles that I gave below. So whenever you're doing control, any method we've used so far involves defining some target poles for your system. All right. If you convert this to a characteristic equation, the roots of this second order equation are the desired target poles. The reason we have this characteristic equation is this is part of... Do you guys remember what this equation is called? This equation for the feedback gain matrix. There's a little hint right here. Yes. It's the Ackermann or Ackermann formula. I don't know it's probably Ackermann. It sounds very German. It's not the same as the Ackermann steering geometry. There's a different Ackermann. I think he's still alive today, but he's very old, and he does control system engineering. But this is his claim to fame. The Ackermann formula is a way to solve for your feedback gain matrix. And this feedback gain matrix is the key to your closed loop system achieving those target poles. Another review question. You see this B-AB matrix in there? What's that called? And we have to take the inverse of this matrix to calculate K. And if you can't calculate the inverse of this, it's something very telling. Do you remember what that matrix is called? If you can't calculate the inverse of it, the system can't be controlled. Yes! This is called the Controllability Matrix. Because in order for your system to be controllable, you have to be able to calculate a feedback gain, which gives you your desired target poles. But if you can't invert this matrix, then you can't solve for that gain. So this is like a check in advance of you even like trying to implement your control system. If you can't invert this matrix, you can't control it. For higher order controllability matrices, is the first term always 0001 in the Ackermann formula? No, this matrix can change in dimension a little bit, but it's still populated with zeros and ones. The purpose of this matrix, so in this case, we just have one input and one output. So the K matrix, well, depends on the size of your states too, but the K matrix is 1 by 2. What is the size in general? Okay, I don't want to waste too much time on this, but we can look at this over here. Your control input, U, is your feedback gain matrix times your states. So your states, we say generally you have N states, and generally you have R inputs. So the K matrix has to be R by N. So the size of this affects the size of this matrix out in front. But we're not going to trouble too much with that in this class. If you use this Acker formula in MATLAB, it takes care of that piece for you. Okay. Now we're getting to the main point that's going to start off this new material today. So your control signal is the feedback gain matrix times your states. But notice that I put a hat on top of this variable because you never know the states in real life. You never know them. Rather, you know estimated states. Like in this particular example, one of the states is the angle of the pendulum. The other state, so the first one, we said it was the angle of the pendulum. The second one is the angular velocity. The angle we measure, but remember, in real life, measurements have some noise. And so we're not really accessing the true angle most of the time. Even if we're measuring a state, we're getting some approximation of it. This one, in this example, we're not even measuring the angular velocity. So this leads me to our next section here. I mean, the control input depends on the states, but we don't really have access to the states. At best, we have a noisy measurement of what we think is the state. Okay, so the control input depends on the states, so how do we estimate the states? First, we're going to show a poor way to do it. Okay, so think about this thing operating in front of you. It's moving back and forth to try to balance this. Assume we have the previous state. Okay, that's going to get to something. That's going to get to something I'm going to mention. You have a sensor like a rotary encoder on here that's feeding you like, okay, I have the angle at this time, and then I'm gathering subsequent angles, and you're like, okay, so I need to calculate my input at this time. I have my gain matrix, so I have these things, and then I can substitute in what you measured here, even though I know it's noisy, but then I have no idea what to put in for the angular velocity. So something you might do, you might say, well, why don't we use our model? Like, okay, I see forward difference. Maybe I'll put a note here. So forward difference would be, I'm gathering a lot of position estimates, and I could say that the time derivative is going to be approximately, like, say my current estimate or my current measurement. I have to keep scooting this thing over. So we know that the time derivative is change in the quantity over the change in time, right? So forward difference is actually a good guess. But let me ask you this. Have you ever, or what happens when you take the derivative of a noisy signal? Like if you do this, but remember in general, like let's say that's the real theta, it's changing with time, it's kind of oscillating. Anytime you like measure it, it's probably going to look more like this. And when you try to take a time derivative of a noisy signal like this, it turns out looking really nasty. Like it might look It'll look even more noisy is what I'm saying. Yeah, you could get the wrong slope because couldn't we apply a filter? That is a good answer. You can. So, okay, you know it's going to be noisy, so you could. Why don't I filter this? And when you filter something, you get a little bit of time delay, so that's why I'm drawing like a little phase delay here. That's going to make your derivative estimate look a lot smoother, but a little bit delayed as well. Spoiler alert, Kalman filter. Okay, well, that's true. A Kalman filter, you guys might have heard that, is the best way to deal with the problem that we're talking about. But you got to crawl before you walk. And we're crawling right now, okay? And I think, my opinion is, whenever you're tackling a new problem, it's better to start with what you know. Dither says best. Okay, a Kalman filter is a very popular and useful tool. Maybe best is too strong. But I think it's good to start with simple things that you know. So I think like looking at this problem and being like, okay, let's do forward difference of the measurements. That's probably a very good place to start, and you might get decent results. I'm going to show you something different. Well, this is related to forward difference. You could say, okay, I want to estimate my states, and I have a model that tells how my states are related to my previous states. So I could do x, k minus 1, and I know what my control input is because I'm the one who's specifying it. All right, and so let's talk about this. This is one way to estimate your states. So use the plant equation. Okay, there's at least two problems. I'm going to give 3, and maybe you can think of even more problems than this. You need initial state estimates to get this started. So this is a recursive equation. And so you're going to have to start this by providing some like prior state. And your state vector is going to look like this, you know, your angle and your velocity. So even at best, you're going to have to guess an initial velocity. So maybe if you have this system right in front of you and you make sure that it starts like upright and perfectly still, then you have a decent like initial state estimate. I know like the initial angle is 0, the initial velocity was 0 because I just held it still. Okay, so maybe you can be like, okay, I overcame that problem. But there's another problem. So we played with a DC motor controller last class, and you designed controllers based on the model, right? But you found that your controller didn't behave exactly like you predicted. And the reason is models aren't entirely accurate. Even with the best intentions and really sophisticated system identification techniques, usually a linear time invariant model, it doesn't capture real life. All right, there's like nonlinearities. Like one of the things that we noticed was there was like this friction in the motor, like this dead zone where when it was moving really slow, you had to build up enough voltage before you could even get it going again, and it kind of did this lurching motion in the ramp response. So all models are wrong, but some are useful. Yes. I've heard, that's a very good quote. Who's that quote from? Okay. Now, that's very true. So even if you have a very good initial state estimate, if you start using this recursive formula, it's going to get more and more off with time, and the error's just going to accumulate. Well, that's not entirely true. If the system is stable, then the transient response of the initial states will decay. But okay, let's do a third problem. Opie, I can turn on and off the chat, but some people found it distracting. So I kind of like to turn it off. Okay, here's the third problem. This model doesn't account for external disturbances. So the only input coming into this model is the control input U, right? But in real life, you might have some external stuff coming in that is outside of the control input. So like think of an aircraft, there's like gusts of wind. Even balancing this pendulum, like in a lot of videos you see, somebody comes up and like taps the pendulum with their hand, and then the system has to react to that. Well, this plant model doesn't include disturbance terms. All right. So there's problems with this. Now, let's talk about a better technique, guys. If you haven't seen this before, it's very cool. So we're going to use an equation that starts off the same way. We're going to use our model because it's, even if it's not totally accurate, it's useful. But we're going to add on this term, minus L times y hat, and I'll explain these terms, minus y. Okay, so first we know what y is. This is your measured output. Okay, y hat, this is our estimated output. And let me define this. This is our output based on our best estimate of the states. So let's assume that the D matrix is 0. So this is just going to be your output matrix times your state estimate. All right. And likely there's going to be a difference between what you predicted the output to be based on your model and what you actually measure with your sensor. I mean, especially because there's going to be some noise on this measured output. Wouldn't that just make the difference your error? Well, this difference is different than the output error. Okay, like your controller is trying to minimize the difference between the measured output and some like reference signal, right? So this is not the reference signal. This is just the difference between what I'm measuring the output to be and what I think the output should be based on my model. Do you get the difference? So it's measurement prediction error. That's a great way. Let's call it that. Jeez Louise. That's a great term. Measurement prediction error. It's like, based on my states and my model, this is what I think my next measurement should be. Okay, but it's off a little bit. What's going on here? There's some error. Okay, and then this matrix is the estimator gain matrix. And it's a lot like, it functions like the feedback gain matrix, basically. Like the feedback gain matrix operates on some output error, like the difference between your reference and what you measure. The estimator operates on the error between what you predicted the estimate, or what you predicted the output to be, and what you actually measured with a sensor. So this term that we added is using information from our sensor to kind of like juggle what we think should be happening from our model and what the sensors are telling us. Can the sign on this gain flip? Yes. Yeah, it doesn't have to be purely positive. Okay, so let's simplify this a little bit. We know that U is going to be minus our feedback gain times our estimated states. So I'm just going to rewrite this but make some substitutions. So this is going to be minus BK times our estimated states, because we don't have the real states, minus L times C minus YK minus 1. And if you were to gather all these estimate state terms together, you have that, and then plus that estimator gain matrix times your output. All right, let me tell you what this gain matrix is all about, and then we're gonna show how it works. So the purpose of L, the estimator gain matrix, is to make the estimated states approach the true states. And you never have access to the true states. But the purpose of L is to try to make those estimated states approach the true states. So the way to show how this works, we have to show that using this estimator equation, that the state estimation error goes to 0 eventually. So let's define the state estimation error. So all it is, let's call it xk K with like a tilde on top. It's going to be the difference between my estimated state and the true state. So you can just call that the state estimation error. The difference between the estimated and the true state. So what I'm going to do, we have an expression now for the estimated state up here. And so I'm going to substitute that into this equation. So A minus BK minus LC times this plus L. Okay, so that's our estimated state. And then our true state, assuming that our model's any good, is A times xk minus 1 So there's our true state. Estimated state minus true state. But even this true state depends on the estimated state because our control input is minus K times our estimated state. Because I don't know my true state, so as this system is operating, it's depending on my estimated states. And this measurement, I want to write this in terms of the true state. So that would be C times my state. And you'll see where I'm going with this. We got 2 more lines to go. And then this is going to look, it's going to blow your mind. That's exactly what it's going to do. Okay, so let's simplify this. I'm going to have A minus BK minus LC, but then I have another x hat term from over here. And it's going to be minus BK times x hat, k minus 1. But there's another minus out in front, so it's going to be plus BK. And then I'm going to have some terms based on my true states. And you probably already see this. These BK terms are going to cancel because I have like minus BK plus BK. And so now look at this. I have A minus LC times my estimated states plus LC minus A times my true states. So this is A minus LC times the difference between my estimated and true state. But this is just, well, that difference, we defined it as the state estimation error. Okay, so here we go. If we use the state estimation equation that we defined at the top of the page, the state estimation error, so the difference between the estimated and the true states, is going to be this. And remember, we want that error to go to 0. Well, to be like a vector full of zeros. So every estimated state is approaching the true state. So now a question for the chat. How can we be sure that the state estimation is going to go to 0, like based on this equation here? Like, what are some conditions you have to put on that equation for that to be true? A equals LC. Okay, if A were to be equal to LC, that would be a 0 matrix times the states. So that would just mean that the error is always 0. But we know that the error is not going to be always 0. Like it's going to start. If you made, I guess maybe you could do that. I won't totally rule that out. But I see some other options. The magnitude of the eigenvalues less than 1. Okay. So this is a more general one. If eigenvalues, or if the magnitude of the eigenvalues is less than 1, we know that this system will be stable, so it'll decay to 0. So this means if you can do that, estimation error goes to 0 eventually. So, based on your model and your sensors, A is going to be given. You can't change that. C is going to be given. So you, as the control system engineer, you have to design an estimator gain matrix so that the eigenvalues of this are less than 1. But we're going to turn this into a controls problem. And this is really cool. Like, you want this error to go to 0, but think about it. This equation looks a lot like like this matrix is our closed loop this one is for the closed loop poles of our system, and we choose K so that our closed loop system has some eigenvalues that we want. So I might be like, I want my system to settle in 1 second, blah, 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 blah. What I'm trying to tell you is we can do the same thing with our estimation error. So we can define estimation error dynamics. By choosing poles for the estimator. And then you carefully craft the L matrix so that you achieve those target estimator poles. It's cool because problems come up in control engineering like this one, like how do I estimate the states? And then the solution that we came up with is to use controls to solve that problem. I think that's pretty cool. It's a controls problem within a controls problem. Okay. Dang it, we're running out of time. Are there singularities? You mean black holes? Sucking matter and light. Okay. Because we're short on time, this next proof, it's good, but it's gonna take like another 20 minutes. What do you guys think? Should we just start it up next time? Or should we forge ahead? If I do it, it's gonna take 20 minutes. You have class at 1. Okay. Some of you have class at 1. So we're going to reserve this for next time, okay? I know some of you, it's no problem to stay, but okay, Alex Wilkins, good question. So do we have all the content in order to do the homework? You do not yet have all of the content, but you have enough to get started, and then the rest of the content you'll get Wednesday. Let's pull this up. Okay. What Alex is referring to is homework 7, which is going to be due next Wednesday. Let's open it up. Now, this homework isn't very long, really. I was tempted to make this due Monday, but it's more appropriate that it's due Wednesday. So we've talked about this antenna system before, but what we're going to do is we're going to use the state feedback controller for this. So I give you a general model for this. And then this is already in discrete time, so you don't have to convert to continuous. So convert this into a state space form. I want you to put it in the controllable canonical form. And then now I give you some parameters to plug in there. And so now it'll be in terms of numbers. And I want you to use state feedback control to figure out what the gain matrix should be so that the system has a settling time of 5 seconds and a damping ratio of 0.8. So items 1 and 2, you can already do. The next item, which is just what we barely touched today, get the estimator gain matrix so that the estimation error settles in 2 seconds and the damping ratio is 0.5. So it's like you're designing a estimator that works with the controller. So it's like the estimator estimates the states that the controller needs. Controlception. Yes, that's exactly what it is. And so a rule of thumb, and I'll talk about this more next time, but because your controller depends on the estimated states, you have to make sure that the dynamics of your estimator are much faster than the dynamics of the controller. So in other words, the estimator needs to figure out the states quickly so that the controller can then use those states to control the system. So like as a rule of thumb, the estimator should be 2 to 6 times faster than your controller. So like the controller settles in 5 seconds. So I made it so the estimator settles in 2 seconds. Okay. Then, last part is you're going to simulate everything. Can I share some reference where you can look more into it? If you have the textbook for the course, which I list on the syllabus, they have excellent descriptions of state estimators. So that's where I would go first. Like the Franklin textbook or the Ogata textbook, they both talk about estimators. Both of them. I like the Franklin. The Franklin textbook's probably my favorite though, because he gives some very intuitive explanations of how this stuff works, and it's. But even if I predictions state estimator, if I just throw that in Google. Sometimes it's also called a sometimes it's also called a state observer. Ah, so if you Wikipedia state observer, yeah, this one, ooh, it's also called a Leuenberger observer. Goodness gracious, who's this guy? Is he still alive? Oh, he's at Stanford. We should thank this cat at Stanford for David Leuenberger. I wonder if they talk about sliding mode observer, multi-observer. A Kalman filter is an observer. So you saw somebody brought that up earlier. If you want to look up Kalman filter, that's like the next level. We probably won't get to the Kalman filter. You guys, if you, over these next few classes, if you find that estimators, if you think they're really cool, you need to take Cressida's courses, because he is like a wizard with Kalman filters, and he's furthered these things in the academic community. That's true. In self-driving cars, Kalman filters are ubiquitous. But at UB, we have like the father of the Kalman filter. I won't call him that, but I mean he's close to like the father. Cressida's. We should like Google Scholar him. But I mean, he has textbooks on estimation, or one textbook. He has all these like crazy publications. Yeah, John Cressida's. Like this book, Optimal Estimation of Dynamic Systems. I mean, this is huge. But a lot of his research is about the textbook on estimation. If you want to know about estimation, yeah, get that textbook. But I mean, his research is all about using these estimators for satellite attitude estimation and control. So he does all this satellite stuff, and he does it for nonlinear systems. If you have any questions about estimation, this guy's like the king. So I'd be remiss if I didn't tell you that if as we get into this stuff, if you're like, ooh, estimation, you have to take his courses. You have to talk to that guy. Dang it, I wanted to get into this this derivation today, but I think it was good to get back some like recap, have some discussion in the chat. So we'll just blast through this next time, keep forging ahead. An idea I had, which would be fun, is we designed controllers for this DC motor using root locus. We could do the same thing with state feedback, and then I can have you guys run those controllers. So this is what I'm thinking. We're gonna have see you, Babu Rao. we're going to have this one homework due on Wednesday of next week. I'm thinking we're going to have one other homework probably due like the last day of class, May 8th. And we're going to have one more project. So 2 homeworks and a project. Maybe one of the homeworks I can make state feedback of that DC motor. What is the course name? The course that Cressidas teaches it's a graduate course called Optimal Estimation. Will we have a final? We're not going to have a final. UB Registrar. Let's look this up. I don't know if he teaches it in the... There's only 3 weeks of classes left. But, so let's say... So we have this homework due on Wednesday, the 29th, right? And then I'll have another homework due the 8th. But then, I'm going to have, like, our third project due after the end of classes. Because we don't have, like, finals week, right? So I'm just going to have... I know, it's crazy. There's only 3 weeks of classes. I don't know what your other professors are doing for finals week and stuff. Let's see if I can find that. Okay, optimal estimation methods. John Cressidas. Oh, it looks like he also teaches it online. So, if you're a graduate student... This is coming up next fall. If you're an undergrad, you probably can't get into it. I know you can take some graduate courses as an undergrad, but maybe not this one. Man, yeah, that's cool stuff. You guys, and if you like controls and you're a graduate student, you should look into taking optimal control with Dr. Singh. That was one of my favorite graduate classes of all time. I loved it. I didn't get an A. I got a B. I worked my booty off. I loved every minute of it. And I got a B. All that to say, just go after stuff that you enjoy. I learned so much. Yeah, we have cool graduate courses on controls. Oh, if you had to pick one, who would I recommend? That's tough. You got to do both. You're leaning towards Cressidas. They're both really good. I don't know. Maybe, like, if you had to take one, maybe Cressidas, just because you know that he's, like, probably, I don't know. He's one of the top guys in the world regarding estimation. I mean, Singh, he's top as well. But Cressidas is, like, without a doubt, the guy on estimation. So if you can learn it from him, do it. I mean, Dr. Singh has done some optimal control theory on his own that's pretty cool. Like, it's related to the fastest way to move a flexible structure from point A to point B. Dr. Singh has done a lot of stuff about that. Falcon says, I would, but I'm graduating, so I can't. I know, there's... At the end of my undergrad, there were so many things that I still wanted to learn. That's one of the main reasons I applied to graduate school, because I was like, holy cats. I'm just getting a taste for, some dynamics, control stuff. Not to say that you have to be in school to learn this stuff, but UB math professor's rating with a party of 7. Welcome to the chat. Should I take any prerequisite before taking a class? Okay. If a good prerequisite for optimal estimation is I think it's called system dynamics. Where are you? I don't see it. Oh, system analysis. You should take system analysis. Are those pigtails? These are not pigtails. These are man braids. I want to learn all this, but I'm worried it's too difficult for me. I mean, controls is difficult, right? But if you really, I would say if you want to learn it, keep forging ahead little by little. Work on the stuff that that you're weak on, and you're gonna keep improving each day. Did you man braid them yourself? No, I didn't. My wife Hannah did these. I need to learn how to do braids myself. Braids they're efficient, man. Your hair doesn't get all tangled. In Russian? Is that what it says? What does that say in Russian? Dr. Estes, with all this cool stuff you mentioned, can you name a couple companies that would want us for this talent? I mean, like, if I'm thinking local, I mean, Moog develops. Welcome, Shot. I don't speak any Russian, but you're welcome to hang out. Moog develops actuators, and there's a lot of control systems theory going on there. Any aerospace company, like Northrop, why are names escaping me right now? Boeing, like definitely aerospace is like a direct application, but autonomous cars, if you're into any, because you're a GM, right? I mean, so even GM is going to be like getting on top of this autonomous car stuff. And it doesn't even have to be mechanical. Like chemical engineers are using these control systems concepts for, the different processes, and that's cool about controls. That it definitely doesn't have to be a mechanical application. You could be doing anything. Lockheed, yeah, yep. Lockheed would. These kinds of skills are definitely in demand with Lockheed. What music is going on right now? That's what I need to know. Ooh. Yeah. You guys just keep forging ahead. Don't be discouraged. Things are going to turn around, so you're welcome, Manny. Do you guys know what this is from? This is one of my favorite video game tracks ever. This one's not Zelda. We've played a lot of Zelda here. Sounds like a Pokemon dungeon. Oh, I should use Google Translate as well. Haven't beaten Majora's Mask. Are you talking about me? I haven't beaten Majora's Mask? I know who you are. Oh my goodness. This isn't RuneScape. Alright guys. I'm gonna show you a picture. This isn't like the best hint because this is an artistic rendition of the game. The game is much lower resolution than this. It's from the 90s. I think 97. I believe this is Emerald Weapon on the right. And these are our heroes on a red submarine. Yes! This is Final Fantasy VII, guys. A remake just came out. I want to play it. You've never played through all of it? So you mean you started it and then what happened? You just gave up? The remake covers all of Midgar. Okay. You decided on grad school over Final Fantasy VII? Why did you do that? That was a mistake. You want to get the remake but only have Xbox. Oh right, it's a PS4 exclusive, isn't it? What was re-released on Switch? Final Fantasy VII on Switch? Oh, the original. Oh, okay. Yeah, I can't see him not bringing it over to the other consoles eventually. Huh. You guys are probably all playing Animal Crossing, aren't you? Square Enix and Nintendo were super tight back in the day. Yes, with all caps. Animal Crossing. My wife Hannah is playing Animal Crossing a lot. She loves it to death. I think it's an amazing game. Animal Crossing, yeah. Do you like Boogie Tea? What's Boogie Tea? Boogie T is an artist, a musical artist. What kind of music? A DJ? Some of it's kind of cool. I'm looking at pictures of this guy. He does look pretty cool. Is he a farmer? I like this style right here. A corncob pipe, overalls, and that's it. Living the dream. Theophany, that sounds really familiar. Spooky Majora's Mask covers. When you played the original Final Fantasy VII, who did Cloud go on a date with? I think it was Eris or Aerith. Right? Did you have a choice? Oh, could you choose like Tifa or something? Oh, it depends on how you play the game. I think mine was definitely Aerith. You can get Barret if you know what you're doing? I wish I had chosen that plot path. Wait, is this when you're in the, what is it called? Like the Golden Corral? And you get in that little pod and you go on this little roller coaster and you see the fireworks and stuff? Gold saucer. Golden. Why did I call it Golden Corral? Buffet. Oh man. Tamba, defeat the evil pigs. I haven't heard of that. Oh, for PlayStation. Oh man. That's taking me back. Oh man. Do you guys... So I played a lot of PS1. And for me, we were all about Siphon Filter. Do you guys remember this? Oh man. That's way back. But Final Fantasy games, that was my jam. RPG for life. Yeah, RPGs. There's something about the story, the feels. What's OOT? Ocarina of Time? Yes. You really like Final Fantasy 15. Have I? Oh. Yeah, I didn't play it. But people rip on it a little bit, right? What is it about it that... Because it was open world. Yes, I'm married. Did anybody like Final Fantasy X too? Oh no. Or also Final Fantasy 12. That didn't get... I don't think that was super popular. I played that a little bit. I never finished it. It's one of the... Yeah, 10-2. Yeah, 12 just... Just felt kind of bland. $13 was real rough. That was the first one on the PS3, right? Final Fantasy 1, 2, and 3. Those were real clunky. They say Final Fantasy 6 is the best of all of them. I haven't played it. But I think that's the consensus, that 6 was the greatest. That's what I heard, that it was greater than 7 even. It's hard to believe. Six greater than 7? I don't like that math. Not everything can be described by math. Zalamar. Description doesn't tell me much. When you say digital controls and engineering, is it like a branch of control systems, or is it something completely different? So it's the branch of control systems working with, well, we're working with linear discrete time systems. So yeah, control systems. We're doing like root locus, control system design, state feedback, controller design, and then just basics like converting from a continuous time to a discrete time system, transfer functions, Z transforms, control system stuff. You're right, digital controls might not be the most descriptive. I should say digital control systems. There you go. Continuous and discrete. right, ladies and gentlemen, I have to head to another online meeting. Zalimar, thanks for the info. I was just unsure if there was some kind of IT field that also worked with that. Yeah, probably. We're doing the control systems theory. So we're, lecture's over today, but Monday, Wednesday, Friday, we go from noon to like 1 p.m. See you later, UB Math Prof. Always a pleasure to have you here. Guys, thanks for hanging out. I'm going to be back for office hours at 3. So you're welcome to join. There's probably going to be some retro music of some sort. I'll take questions and whatever. And that's what we're doing. See you guys.